Okay, so year 12. Today we're going to make a start on some of like the year 13 content, so some of the content from the year 2 textbook. I know a couple of you haven't got a copy of it yet, but I'll sort something out about that, so do not worry if that's the case. So to start with, chapter 1. Most of the chapter is to do with algebraic fractions, and it's going to kind of feature new stuff on algebraic fractions that you've not seen before. So part of it is going to be this. So stuff to do with adding, subtracting, multiplying, etc. algebraic fractions. This bit should all be reasonably straightforward. I think you're all going to be excellent at that. And then there's this, which is new, which is using partial fractions, but is exciting and good. And then this here, also to do with algebraic fractions. But the first little section of this chapter is on proof by contradiction, which is, I think, reasonably difficult. Not so much in terms of like the actual like doing really hard questions. It's just the questions are quite hard. The way you have to think is quite hard, and it's not quite as here's a method, this is the method, you need to just do this method. It's much more you need to think really carefully about what you're being asked. So don't let that put you off. This will be difficult, but we are going to get there. Okay, so year 12. In terms of proof by contradiction, then you'll have done proof kind of at GCSE and a bit in year 12. I think you might be doing it at the moment. We're going to see some Blake, I'm not quite sure. But the kind of proof questions you'll have looked at up to this point would be things like prove that the difference of the squares of two consecutive even numbers is always divisible by 4, that sort of thing. Now, proof by contradiction is like a new method of proving things, and it requires 3 very, very specific steps, and it requires you to kind of show like your proof in like a really specific logical way. So the 3 like basic principles of proof by contradiction are up here. Let me just change to my pointer. So to prove a statement is true by contradiction, we assume that the statement is actually false. We make an assumption that the original statement is false. After this, we show that that would lead to a contradiction. Now, if that leads to a contradiction, we must have been wrong in assuming the original statement was false, and therefore the original statement must be true. So this here is like a kind of a really straightforward example in like of the sort of thing I mean. So prove that there is no greatest odd integer. So step 1, we need to assume that this is false. If this is false, so if it's false that there is no greatest odd integer, we assume, and it's good to use that word in your proof, so assume that there is a greatest odd integer, and we can call that greatest odd integer n. So that's like the first bit done. Then we need to show that they'll prove that this would lead to a contradiction. So this bit here is normally like the hard bit of any kind of proof by contradiction problem. But here, the way we could do that is like this. Well, if n is the greatest odd integer, then n plus 2 is also an odd integer, and that is larger than n. So because of that, this contradicts the assumption that n is the greatest odd integer. And so finally, you write your conclusion, and your conclusion is therefore, so we just write now the thing that we were trying to prove, therefore there is no greatest odd integer. I'd really recommend that you take like a note of the contents of this box now, because this is how you should be structuring your proof, and these are like the words you should be using. Often students kind of like know what they mean but aren't communicating it in a mathematical way, and you're not going to get marks. So you need to structure it in this way. So kind of statement 1 would be assume that, and then you say what you're trying to assume, which is like the opposite. You then do your reasoning, and so your reasoning is often like a bit more mathsy, it looks a bit more algebraic. And then you might say this contradicts the assumption that, and state what it contradicts, or say this is a contradiction. And then finally, you need to conclude, so you need to write therefore and restate your original statement. We're going to go through kind of 3 different examples, and they are quite different, of proving things by contradiction, and that will be in this video and the next video. But just before we get on to kind of more complicated mathematical proofs by contradiction, it's really useful just to test this one skill here, and this one skill, is negating the original statement. So the first part, like stage 1 of a proof by contradiction, requires you to negate the original statement. So it's like the opposite. So here, statement 1, there are infinitely many prime numbers. Now the negation of that would be, let me just switch pen, there are finitely many prime numbers. Okay, because if there's infinitely many, the negation would be that there's finitely many, they don't go on forever. This one here, the middle one's a little bit harder. So the middle one says all popes are Catholic. We need to find the negation of that. And the negation of that is there exists a pope who is not Catholic. It's not saying, the negation is not no popes are Catholic, but it's kind of saying at least one pope exists who is not Catholic. That would show, that would be the negation of that statement there. So like the way you can remember that, and maybe worth taking a note of this. So the negation of all are is not actually none are. So the negation of everyone likes green isn't no one likes green, but it is kind of a not everyone likes green, or there is at least one person who does not like green. Then this final one is an example of like a conditional statement. So the conditional statement is if it is raining, my garden is wet. Okay, we need to think about how we can negate that to change its meaning. So we've got if it's not raining and my garden is dry, it's not raining and my garden is wet, or it's raining and my garden is not wet. Now it's going to be this last one here, okay? And that would negate the original statement, because the original statement is if it's raining, my garden is wet. Now this is saying if it is raining, but my garden is not wet, and therefore that's a negation of this bit here. So when you've got a conditional statement, so something like if A, then B, the negation is A and not B. So A is true, but B is not. That's how we negate. So what I'm going to do now, I'm going to put this together with like my first formal proof by contradiction, and then there'll be a separate video with 2 other proofs by contradiction. This will probably be quite difficult, and you will find it, I don't know, I'm kind of guessing, I won't obviously have seen it all. I think a lot of you will find this quite difficult. Like, please do not panic, like we will get there, we will go over this when we are back at school, etc, etc. But just have a go, try and follow through the examples, take lots of notes, and then have a go at exercise 1A in the year 2 book. Okay, so year 12, first example in full of proof by contradiction. So we have got here proof by contradiction that if n squared is even, then n must be even. So step number 1 is to make an assumption, okay? So this is always our first step, is we need to make an assumption. And our assumption is going to be like the negation of this statement. So we are going to assume that there is a number, that n squared would be even, but n is not even. Okay, so if n squared is even, then n must be even. Then like the contradiction would be that there is, assume that there is a number, you write this out, assume that there is a number n such that n squared is even, but n is odd, or n is not even, doesn't matter. Okay, so this is our assumption step. Now we've made our assumption step, we need to show that this assumption leads to a contradiction. So we need to show the contradiction. Now this is like the hard part, and there's not like a straightforward way, and it will depend a lot on the specific thing you're trying to prove. Often you'll go wrong at the beginning, or you'll try something and it won't lead you anywhere useful. But here, right. So we're assuming there is a number n such that n is even, but n is odd. Now, if n is odd, okay, so if n is odd, then we can write n in the form 2k plus 1 for some integer k. And that's quite a useful, like, general principle. Okay, and that makes sense because whatever number k is, n would be an odd number if it's 2k plus 1. So therefore, if we did n squared would be 2k plus 1 squared. 2k plus 1 squared is 4k squared. plus 4k plus 1, and this is getting to look a bit more like a kind of familiar proof type thing. We can then write this in the form 2 brackets 2k squared plus 2k plus 1, like that, and this is odd. So this here is odd. And we know that this is odd because this bit is 2 times something, which is even, and an even thing plus 1 is odd. And so now, being really careful to actually show your contradiction, we're going to write out explicitly, this shows, no it doesn't, this contradicts the assumption that n squared is even. And then finally, we need to just go to our conclusion stage. So our conclusion stage therefore, and just think about what we've done already. If n squared is even, n must be even. So we're restating the original thing we were trying to prove. And it's really important you do that. And I'm just going to finish off my proof by doing that box, which means I've proved it. We're done now.